Today we'll talk about common sense reasoning. You and I, as cognitive agents, are very good at common sense reasoning. We can make natural, obvious inferences about the world. How can we help AI agents make similar commonsensical inferences about the world? Suppose I had a robot and I asked the robot, find the weather outside. I don't want the robot to jump out of the window to see whether it's raining outside. But why should the robot not jump out of the window? What tells it that it's not a very commonsensical thing to do? We'll talk about common sense reasoning using a frame representation. We'll start talking about certain small set of primitive actions. There are only 14 of them, but they bring a lot of power because they organize a lot of knowledge. These primitive actions can be organized into hierarchies of sub-actions. These actions can result in changes in the state. This is important because that is what allows the robot to infer that if I were to take this action, that result might occur, that state might be achieved, so that it decides not to jump out of the window because it might get hurt.
Okay, have you ever wondered how you could write the equivalent of a Watson program or a Siri program for your own computer? Just imagine if you could talk to your machine in terms of stories. Simple stories, perhaps just one-sentence stories like Ashok ate a frog. Now, we have already seen how a machine can make sense of this particular sentence, Ashok ate a frog. We did that last time. But of course, eat or ate can occur in many, many different ways in sentences. Here are some of the other ways in which I can use the verb eat. Ashok ate out at a restaurant. I could tell something was really eating him. Now, the sense of eating him here is very different from the sense of eating here. There is no physical object that is being eaten here. The manager would rather eat the losses. So now this is a very different notion of eat. The river gradually ate away at the riverbank, yet another notion of eat. So just like we had in the previous lesson, take, the word take, which had so many different meanings, eat has so many different meanings. Now when we were discussing the word take, we discussed how we can use both the structure of sentences as well as background knowledge to disambiguate between different interpretations of take. We could do something similar with eat. We could enumerate all the different meanings of eat, and then for each meaning of eat, we could ask ourselves, what is it about the structure of the sentence, and what is it about the background knowledge that I have about things like rivers and river banks, which tells me what the meaning of ate here is. To summarize this part, if you were to start talking to your machine in stories, in terms of simple stories designated by a single sentence, then one problem that will occur is that words like ate or take will have large number of meanings. And we have seen how your machine can be programmed in such a way so as to disambiguate between different kinds of meanings of the same word. Now here is a different problem that occurs. Consider a number of stories again. Each story here is designated by a single sentence. Ashok ate a frog, Ashok devoured a frog, Ashok consumed a frog, Ashok ingested a frog, and so on. Several sentences here. Now if you think about it a little bit, each of these sentences is using a different verb, but the meaning of each of these verbs in these sentences is pretty much the same. So that Ashok ingested a frog, or Ashok devoured a frog, or Ashok dined on a frog, practically the same thing happened in each case. There was a frog which was initially outside Ashok's body, and then Ashok ate it up, and at the end the frog was inside Ashok's body, and the frog was dead, and Ashok was happy. So the next challenge becomes, how can a machine understand that the meaning of each of these words here is exactly the same? In a way, this problem is the inverse of the problem that we had here. Here the problem was that we had a single word like eat, which had a lot of different meanings in different contexts and different sentences. Here, the issue is that we have a lot of different words, but they have the same meaning given the context of the sentences. So another question then becomes, well, how can we make machines understand that the meaning of these words in these sentences is exactly the same? Each of the sentences is telling us exactly the same story. There is one other thing that is important here, and that is the notion of context. One of the hardest things in AI is, how do we bring context into account? In both of these cases, context is playing an important role. On the left side, context is playing an important role because we understand that the meaning of eat is different in these different sentences because the context of eat is different. Here, context is playing a different role. We understand that the meaning of each of these words is practically the same because the context here is practically the same. A couple of quick qualifications here. First, right now we're dealing with stories that have just one sentences. Very soon in the next lesson, we'll deal with stories which are much more complicated, which really have a series of sentences. For now, just simple stories. The second is that here the structure of all of these sentences is the same. So structure practically tells us something about the context. But the situation is a lot more complicated because often two sentences which have very different kind of structures can still have the same meaning. So consider these two stories. Bob shot Bill and Bob killed Bill with a gun. Now here the sentence structures are very different, but their interpretations, their meaning are the same. Bill was the one who got killed, Bob was the one who did the killing, and the killing was done by putting a bullet into Bill. So the question now becomes, how can we build AI agents that can meaningfully understand stories like this one, and stories of the kind that Bob shot Bill and Bob killed Bill with a gun? One thing we could do is that for each of the verbs here, we could have a frame like we had a frame for take. So we could have a frame for ate, a frame for devour, a frame for consume, a frame for ingested, and so on. Well, we would have a lot of frames then, because there are a large number of verbs in the English language or in any other modern language. Perhaps we could do something different. Perhaps we could look that there is a similarity between the interpretation of these things. Perhaps we could use the same primitive action for each one of them. So when we talk in English language, we might use for communication purposes all of these words. But perhaps we could build AI agents that have a single internal representation for each one of them. What might that internal representation look like? We will call that internal representation a primitive action. Each one of these is an action, but many of these actions are equivalent in terms of our interpretation of those actions. Let's see what these primitive actions might look like. Here is a set of 14 primitive actions that Roger Schank proposed quite a while back. Actually, he used different names for these primitive actions. This is a modern interpretation. Let's walk through these 14 actions very quickly. So move body part is where Ashok might, for example, move his hand from one position to another position. Move object is where Ashok may move an object, let's say a car, from his office to his home. Expel is when Ashok might exhale. Ingest is when Ashok might eat something, and so on and so forth. Propel is when Ashok might kick a ball. So right now Ashok's body is in contact with the ball and the ball is being kicked. Notice that some of these primitive actions have to do with mental actions. So think about or move concept or conclude or feel. So move concept is where Ashok gave the idea to Susie about going to a movie. Conclude has to do with decision making. Think about is just forming an idea inside one's mind. Some of these have to do with percepts and sensors, see, smell, hear. Now, these 14 primitive actions form an ontology of actions. What is an ontology? We have come across this notion earlier. An ontology is a specification of a conceptualization of the world. There is the world outside. We hear or read stories about the world all the time. These stories help make sense of the world, and these stories then use different kind of categories, different kind of concepts. Those concepts in AI need to be specified very, very precisely, and when we specify those concepts in terms of which we make sense of the world, we get an ontology. So here is an ontology. Here are the 14 basic concepts, the 14 basic categories of primitive actions in terms of which we'll try to make sense of a large number of stories about the world. Now you might say that these 14 primitive actions don't cover all the possible stories in the world, and that's probably true. You might also say that you can come up with a different ontology with a different set of primitive actions, and that might also be the case. So some of you may want to try your own hand, come up with the ontology. That's not the point. The point here is that we can now come up with an ontology of primitive actions and program AI agents using that ontology so that the AI agent can now understand a very large number of stories, and that's powerful.
So Ashok, one common story that comes to mind that looks like it would be difficult to put in terms of these primitive actions is something like, I walked across the room, in which case I'm the one doing the moving, but I'm also the one being moved. How would you put that in terms of these primitive actions?
David, that's a good point. One way of capturing the meaning of that story in terms of these primitive actions is to use the move object primitive action. So here both the object being moved and the mover of the object is the same, I. So I am moving myself one place to the another place. I think David's point here is that these primitive actions will be able to capture the meaning of some sentences in a very simple, logical, intuitive sense. And for some other sentences, it might be a little bit more involved. So let us see how these primitive actions may actually help an AI agent make sense of stories. So here is the first thing we can do. Recall there were a large number of stories, each expressed by one sentence. Ashok ate a frog, Ashok devoured a frog, and so on. So now ate, devoured, consumed, ingest, partook. We can think that each one of them really is an instance of a primitive action called ingest. Here is the primitive action ingest. So Ashok ingested a frog here, Ashok ingested a frog here, Ashok ingested a frog here. While superficially these particular sentences are different, in terms of their deep meaning, the deep meaning is pretty much the same. It is true, of course, that devour may have a slightly different interpretation than dining. Devour might be something that I ravish with my hands, for example, and dining might involve fine dining with silverware. Nevertheless, ingest captures the basic meaning of these sentences. What is the basic meaning? The basic meaning, again, is that Ashok is an agent. Frog is the object that is getting eaten, ingested. Initially, the frog was outside Ashok's body and probably dead or alive. We don't know its state. After the ingestion has occurred, or devoured has occurred, or consumed has occurred, the frog is inside Ashok's body and it's dead. And further, that Ashok probably is happy at the end of this particular ingestion. Where is all of that knowledge coming from? It's buried inside the frame for ingest. So each of these primitive actions has a frame corresponding to it. And we have come across frame many times earlier in the class, so by now you should know what it means. And the frame has a large number of slots like agent, co-agent, object, beneficiary, and so on. And those slots deal with stereotypical situations and have default values already put in there. So when a sentence comes like Ashok ate a frog, then the verb ate here pulls out the primitive action ingest and the frame for this primitive action, and the processing becomes top down, and I start thinking, where will Ashok go, where will frog go, who is the agent, who is the object, and so on. Okay, I hope you're enjoying this particular lesson, because I certainly am. Let's see whether you're also understanding this lesson. So here are 4 sentences. John pushed the cart, John took the book from Mary, John ate ice cream with a spoon, John decided to go to the store. And here some of the words are in these blue boxes. For each of the sentence, find the primitive action that would best capture the meaning of the verb inside the blue box. David, what did you think?
So for the first sentence, I debated for a minute between propelled and move object. If John's pushing the cart, it seems fair to say he's moving the object. But the connotation of pushing the cart is that he's just launching the cart into motion. We don't really know where he's moving it. So I decided that propelled is the better answer there. For John took the book from Mary, it suggests that the book used to be in Mary's possession and now it's in John's possession, so we've moved possession of the book. For John ate ice cream with a spoon, it's very straightforward from our earlier example that John ingested ice cream with a spoon. The fourth example is a little bit more complicated as well because it's an action going on inside John's own mind. But if John decided to go to the store, it suggests a final step of a thought process rather than an ongoing process. So I said John concluded to go to the store instead of thought about.
That sounds right, David. There's sort of several other things to note here. One is that the last sentence here has 2 verbs in it, decided and go. And we'll see in a minute how we can deal with sentences or stories that have multiple verbs in them. Second, you're right in that sometimes it's not very easy to decide which is the best primitive action for capturing the meaning of a particular verb here. So the verb here was pushed, and the reason David picked propelled over move object is because in propulsion, the body is in some sense in contact with the particular object that is getting moved. Now, we have not shown here the detailed specification of each of one of these primitive actions, but I can tell you that the readings at the end do give them in detail. So let us dig deeper into how the AI agent might actually do the processing using these primitive actions. So consider the sentence, John pushed the cart. The AI agent begins left to right because we're talking about English language here. The first word here, John, is not a verb. So the AI agent, for the time being, puts this in a list of concepts and ignores it. It comes to the second word in the sentence, which is pushed. There's a verb here, push. And now the AI agent uses this particular verb, push, as a probe into its long-term memory. So now the frame for propel is going to get pulled out. Let's see what that frame might look like. So here is the frame for propel that has been pulled out of the long-term memory. And this frame tells us that we can expect an agent, we can expect an object, and indeed, although we have not shown here, this frame may have additional slots and perhaps additional things can be expected. Now for each of the slots, there is a rule buried in here. A rule which tells us how can we pull out from a sentence the entity that goes under the slot, the filler that must go here. So here is a rule which says that if there is a concept just before the verb, and that concept is animate, then whatever that concept is, put it here. Well, there is a concept just before push, that's John. And let's suppose that we have a lexicon which tells us that John is animate, then we'll put John here. Similarly, there is a rule here for this slot which tells the AI agent that if there is a object, there is a concept that comes after this verb, and that particular concept refers to an object that is inanimate, then take that particular thing and put it here. And that's the cart, and so we put cart here. So this way, this particular scheme helps us derive the meaning of John pushed the cart. And notice that the processing is a combination of bottom up and top down, as we discussed earlier. It begins bottom up because we are looking at the data. Right now we don't have knowledge. But as soon as some data is processed, it pulls in knowledge from memory, and soon the processing becomes top down. This frame helps us generate expectations and help pull things out. This is almost acting like a hook for a fish. So once you have the hook, then you can capture the fish well. So several other things to be noted here. First, representations like this are called structured knowledge representations. There is not only representation here, but there is a strong structure to it. Earlier, when we were discussing predicates and logic, or we're discussing rules and antecedents and consequent of rules, they are like the atoms of knowledge representation. They don't have much structure. But by now we have this molecular forms of knowledge representation in which a large number of atoms are getting connected with each other. And those connections are important because once you have that structure of the molecule, it tells you what can go in the place of each atom. Second, this was a simple sentence, and so the processing was quite simple. These sentences need not always be as simple as this one. What happens if the sentence has a word push in it, and I pick a frame that is not the right frame for it? Suppose I had pulled out a frame for move object instead of propel here. Well, one possibility is that if I were to select a different frame for making sense of this particular sentence, then as I try to fill the slots of this particular frame, I will find a lot of difficulty, in which case I might abandon that frame and try a different one. The second possibility is that I may even force the interpretation of this into the slots of the other frame. But if there is a story here which contains large number of sentences, then soon I'll realize that that is not the right frame. I may abandon it and pick a different frame. So for complex sentences, this processing is not as linear as we have pretended it to be right here. It is also possible that sometimes one of these words may map into two frames equally well. Indeed, this is the basis of many of the puns that we encounter. So consider, I was wondering why the ball was becoming bigger, then it hit me. Now you of course understand that the word hit there, that particular verb maps into two different interpretations, and that's why it is interesting and funny. So here is another one. Two men walked into the bar, the third one ducks. Now here the bar is overloaded. So here walked into the bar is getting interpreted in two different ways. Indeed, people have tried to build accounts of humor based on the kinds of story interpretation that we are doing here. Could it be that this is the beginning of a theory of humor, of how you can tell stories not only to your machines? Let's do an exercise together. Here is a sentence. John took the book from Mary. For this sentence, first write down the primitive action that best captures the meaning of the sentence, and then write down the fillers for each of the slots of this primitive action. What did you write, David?
So for the primitive for this sentence, I chose, as I did before, move possession as the best primitive. I think it captures the high-level meaning of the sentence, which is that we're actually talking about a transfer of ownership of the book from Mary to John, even if only temporary. It might be tempting to think of move object as filling this primitive, and indeed it's hard to picture John taking the book from Mary without moving an object, but move object doesn't capture the highest level meaning of this sentence. John could move Mary's book without actually taking it from her. So instead, move possession is probably the best way to capture the high-level meaning of this sentence. Given that primitive, we can go back to the rule that Ashok was mentioning earlier, which is if we have an animate agent immediately before the verb, we can infer that that agent is the one executing the action. So John here is the agent doing the move possession action. Similarly, we can say that if there's an inanimate object immediately after the verb in the sentence, then we can probably infer that that's the object that is actually being taken. So book becomes the object. Now, if we recall way back in the previous lesson, our list of the way that different prepositions constrain the meaning of a sentence, we can remember that from usually indicates that the word that immediately follows it is the source for some action. Here we have a slot titled source, so we're looking for a source. We have a preposition that indicates what follows is a source, so we can infer that Mary is the source from which John gets the book.
That's good, David. Notice how lexical, syntactic, and semantic analysis all coming together here. The driver is semantic analysis. The driver is this frame which captures the semantics of this particular sentence that allows us to draw inferences about it. That's why we're using the term semantics here. So the semantics is being captured by this frame with terms of all of these slots. But how do we decide on the fillers? Well, that requires lexical analysis and syntactic analysis. So when we have the word John here, John is a concept, and that concept is inanimate, and that information is coming from a lexicon. That is the lexical analysis. And when we have a sentence like John took the book from Mary, and from is a preposition and Mary follows immediately after that, this is capturing part of the syntax of this particular sentence. And that is how we derive that the source must be Mary. So the semantic, lexical, syntactic analysis are all working together here. Notice also how frames and rules are coming together here. We've seen how frames help us understand the meaning of the stories, and that is being done in part by the rules that are buried inside the slots. So there is a rule here which tells us how to extract the agent from the sentence and put it inside the slot. Similarly, there is a particular rule here and a rule here, and each one of these slots may have its own rule. Of course, as these sentences become complex and these frames become complex, these rules will become much more complex, and sometimes there will be multiple rules here and multiple rules here, and this can become very complex very soon. Another point to notice here is that this is capturing the semantics, like I said earlier. And how do we know that? Because I can ask questions. Who has the book? Who had the book? What did John take from Mary? And you can answer all of these questions using this frame. Once you have this frame, question answering becomes possible. Common sense reasoning becomes possible. The relationship between the structure of the sentences and background knowledge is very intricate and complex and very interesting as well. Sometimes the structure of sentences that we use to tell stories have only implied actions in them. Consider the sentence, John fertilized the field. Now, it's hard to see fertilize mapping into any of the primitive actions that we had here. There is an implied action here that is not specified in the structure of the sentence here, but that is much more meaningful in terms of the background knowledge that we have of those primitive actions. What John fertilized the field really means is that John put the fertilizer on the field. Now, put is something that maps into primitive actions very easily. So this points to another feature of the processing. Initially, the AI agent may start with the verb given in the sentence and try to map into primitive actions. And if that fails, then the AI agent may start thinking in terms of how to transform the sentences to bring out implied actions that can more easily map into the primitive actions. This, again, is common sense reasoning. Through common sense reasoning, I'm interpreting that there must be an implied action here that captures the meaning of the sentence. Once I have made the implied action here transparent, then the rest of the processing is easier. The put action maps into the primitive action of move object, this frame is pulled out, and the rest of the slots can be filled in like earlier. Let us do an exercise together. So consider the sentence, Bill shot Bob. Once again, shot is a verb here that does not quite map into any of the primitive actions clearly, cleanly. So perhaps there is an implied action here. So first write down this sentence in terms of a primitive action, then write down the frame from this primitive actions and fill the slots. What did you write, David?
So I rewrote the sentence as Bill propelled a bullet into Bob. I looked at the verb shot and decided what that really means is pulling the trigger on a gun, which results in a bullet being propelled at high velocity out of the gun's barrel. So it's fair to say that shot becomes propelled a bullet. Given that, I now have propel as my primitive. I have the same rule that says an animate agent that immediately precedes the verb becomes the agent in the frame. So Bill is now my agent. I have my rule that says an inanimate object that immediately follows the verb becomes the object. So bullet is now my object. Even though bullet wasn't in the original sentence, it's by rephrasing it that I can pull that object out. And I can use the constraints of into to determine that the destination of the bullet is inside Bob.
That's good, David. But note that the sentence could have another interpretation also. Imagine that Bill had a camera and Bill was simply taking pictures of Bob.
That's true, Ashok, and I bet if we had used Bill takes a picture of Bob as the meaning of shoot earlier in this lesson, that's probably what I would have thought of first. If I wanted to then put Bill shot Bob in terms of taking a picture into this form, I'd first rewrite it as Bill took a picture of Bob.
That's really interesting, David, because notice if you say Bill took a picture of Bob, it's not clear into what primitive action will this took map into. Perhaps we can discuss this more on the forum. There's one more thing to notice here. Like David says, I can have multiple interpretations of Bill shot Bob. This sentence doesn't help me resolve between those interpretations. Perhaps there is something coming before this sentence in the story or something coming after that that will help me disambiguate. From this sentence itself, we can simply construct two particular interpretations. We had said that the title of this lesson is Common Sense Reasoning. Let us dig a little bit deeper so that we can see where the common sense reasoning is coming here. Consider this sentence, Ashok put the wedge on the block. Imagine an AI agent that pulls out the frame for move object as a primitive action and fills in all of these slots, and by now we know how the agent can do that. If I would ask the AI agent, did Ashok's hand move when he was putting the wedge on the block, I would expect the AI agent to say yes, because that is what happens when people move the wedge to the block. They grasp their hands around the wedge, they move their hand, and then they release their fingers. Now, this is what common sense reasoning is about. Making inferences that are not necessarily part of the input sentence here, but are part of the background knowledge that the agent has, so the agent can make inferences about the world, common sense inferences about the world. So the question then becomes, what is the knowledge that the AI agent must have so that it can in fact make the kind of inferences that we are talking about, common sense inferences? Suppose that the AI agent had not only knowledge of the primitive action move object, but also about some of the sub-actions. So here are some of the sub-actions for the given context. So in the context of moving wedges and blocks, the agent might already have a kind of micro story, which says that when actions get done and things get moved from one place to another place, then typically fingers are first closed around the first object, then the hand moves, and then the fingers are released around the second object.
So Ashok, if we can decompose move object into a series of move body part actions, was move object really a primitive action?
That's a valid question, David. Move object was indeed a primitive action related to the various superficial forms in which words can occur in a sentence. As an example, transported, carried, or moved. However, this primitive action move object can have its own story in terms of further decomposition. Notice this particular decomposition, this particular story is specific to the structure of the sentence where Ashok puts the wedge on the block. This raises lots of hard issues. How many such stories are there? Do we have a story? Must an AI agent have such a story for every single situation that it encounters? Those are hard questions. It is not clear that AI currently has an answer to all of those questions. So this theory by no means covers all stories. Many of these stories are beyond the scope of this theory. And in fact, even for the stories that are within the scope, there is a hard question about computational tractability because a number of such stories can explode very quickly. Nevertheless, let us continue and see how else this theory enables common sense reasoning. So consider this sentence, Ashok enjoyed eating the frog. So not just Ashok ate the frog, Ashok enjoyed it. How do we make sense of this term? Once again, because of the verb eat, we may have the primitive action for ingest. Here is Ashok as the agent, frog as the object. And this time, we'll have another slot called result, which shows what happens when Ashok eats the frog. We'll call this frame a state change frame, where there was some initial state and some state at the end of this particular action, the action of ingest. So here, there's Ashok's mood, which is becoming happy.
So Ashok, how would the agent know that in this case the verb we're going to key on first is eating instead of enjoyed?
Good point, David. So we can imagine a different action frame for feel because of enjoy being a feel. The agent is Ashok. Ashok is the one who is doing the feeling, and the object or the feeling that is being felt is joy. We can still have a frame for eating, and we can relate those two frames. So what specific interpretation an AI agent will make this particular sentence will depend on the precise rules that we're going to put into these slots so that the AI agent can make either this interpretation or that interpretation. We will see another example of this situation in just a minute. Sometimes it might not be clear to what exactly does this particular verb correspond to. So consider Susan comforted Jing. Well, what exactly did Susan do to comfort Jing? It's not at all clear. Not clear what the primitive action should be. Although we may not understand what exactly is the primitive action here, We want AI agents, nevertheless, to do common sense reasoning. Their interpretation might be incomplete. Its interpretation might be partial. Nevertheless, you and I as humans understand something about Susan and Jing here, that Susan, for example, did something that made Jing happier. We want the AI agent to do the same kind of reasoning without knowing what exactly is the comforting action here. So we may have a generic primitive action of do. This generic primitive action, we'll use it whenever we are unable to decide, whenever the AI agent is unable to decide what exactly is the primitive action that should be pulled out. So the AI agent may simply say, well, Susan did something that made Jing's mood happy, and this is as much interpretation that the AI agent might be able to do this sentence, which is a pretty good interpretation. Earlier we had promised that we'll deal with sentences which have two verbs in it. So here are two verbs, told and throw. Maria told Ben to throw the ball. How might an AI agent make sense of this particular sentence? So once again, the processing starts from the left. Maria is not a verb, so that's put in a concept list and for the time being ignored. The processing goes to the second word, which is told, which is a verb. And so the primitive action corresponding to told is pulled out. The primitive action is speak, and so now we can start putting in the fillers for the various slots. So the agent is Maria, and the result is, now we go to the second one. Here the primitive action is propel because we have a throw here, and the propulsion is being done by Ben, and the object is ball, and now we relate these two. The second frame is a result of the first frame's action. So if we go back to the previous sentence, Ashok enjoyed eating a frog, we can see how we can represent both verbs there in terms of action frames. So Ashok enjoyed, that might be the frame here. The primitive action is feel, the agent is Ashok. Ashok ate a frog, that's the primitive action of ingest, agent is Ashok, and the object that got eaten was frog. And the result of that is this frame where Ashok had a feeling of enjoyment. Note that some problems still remain. It is still difficult to figure out exactly how to represent a sentence like Ashok enjoyed eating a frog. There can be two representations for that particular sentence, either in terms of two action frames or one action frame and one state change frame. Some of these questions will get answered when we stop thinking in terms of stories that are only one sentence long, but stories that have a number of sentences, stories based on a discourse. Because some of these ambiguities will get resolved when we know more about what happened when Ashok enjoyed eating the frog, what came before it or what came after it. So let's do a couple of exercises together. Here are two sentences at the top. Anika decided to have a glass of water and Mark loved watching TED Talks. Please write down the action and the state change frames that will capture the meaning of the first sentence and the meaning of the second sentence. How did you fill these frames, David?
So for the first one, I did what we talked about earlier. I just started at the left. Anika is an agent, so we're just going to store that away for a little while. And the first verb we encounter is decided. Earlier we said that decided corresponds to the conclude primitive action. So our primitive here is going to be conclude. The animate agent immediately preceding conclude is Anika, so our agent is Anika. The result of this decision is a new action. Our primitive here is now ingest. Our agent is Anika because we're going to infer that Anika is the one having the glass of water because she's the one who decided to have the glass of water. And the object that is being had is the glass of water. So the first action, Anika concluding, caused the second action, Anika ingesting a glass of water. So for the second sentence, Mark loved watching TED Talks. The action that Mark is really completing here is this watching action. So our primitive here is see. Mark is the one seeing TED Talks that we discern by the same reasoning as earlier. The verb loved here tells us something about the change in Mark's mood when he watches TED Talks. So that means that the result of this action of watching TED Talks is that Mark's mood gets happier.
That's good, David. Note though that this sentence is a little bit like Ashok enjoyed eating the frog. This is one representation for this sentence. On another representation, we may have two action frames, one corresponding to the verb loved, another corresponding to the word watching, and then connect them to the slot result. I hope you can see how AI agents might be able to understand simple stories. In fact, this is quite similar to the way Watson and Siri go about understanding the stories that we talk to them. Almost surely the human interactions with the machines of tomorrow will not be based on the keyboards and mouses that we have today. We'll talk to the machines will talk back to us, and when we talk to the machines, we'll be telling machines stories. Stories like Anika decided to have a glass of water, or Ashok enjoyed eating the frog. And when we tell these stories will have context, they will have ambiguities. And we would expect the machines to do common sense reasoning. The power of this particular lesson lies in the beginning of a representation that enables that particular kind of common sense reasoning. We'll continue this discussion about common sense reasoning of more complex stories in the next lesson.
So how would you use common sense reasoning to design an agent that could answer Raven's progressive matrices? Here you might make two connections. First, you could connect primitive actions of agents to primitive transformations in these matrices. Different problems could be composed out of a finite set of possible transformations. What would those primitive transformations be? And what would the action frames involved in each transformation look like? Second, you might connect those individual primitive actions to higher level transformations. What would your primitive transformations be, and what common higher level transformations are possible? What primitive actions would result in those higher level transformations? And how would composing these like this actually help you solve Raven's progressive matrices in a way that you couldn't do otherwise? So today we've talked about common sense reasoning. Broadly, common sense reasoning gives us a formal structure to interpret the world around us. Having that formal structure lets us build agents that can then do the same. We started off with primitive actions, which, like primitives in programming, are the simplest things we can interpret about the world. Then we looked at composing those primitive actions into bigger actions for a hierarchical, abstract view of the world. We then looked at how those primitives can cause state changes, which let us predict the effect or cause of certain events. Next time, we're going to compose these simple frames into much longer stories called scripts. Scripts help us make sense of complex repeated events with relative ease and generate expectations about the world around us.
The connection between common sense reasoning and human cognition is both very strong and not yet fully understood. Let us suppose that I were to ask you to go find the weather outside. You would not jump out of the window. Why not? You would use common sense reasoning to know that jumping out of the window to find the weather is not a good idea. But what is it that tells you not to jump out of the window? You use some notion of goal, some notion of context to decide what not to do and what to do. We use similar notion of context in order to do natural language understanding. We could use context to disambiguate between various meanings of take. Can we use context also to decide on what would be a good source of plan? So far we have been talking about making common sense inferences about physical actions. What about the social world? You and I also make common sense inferences about the social world around us. One possibility is that you and I have a theory of each other's mind. This is actually called the theory of mind theory. According to this theory, you and I as cognitive agents ascribe goals, beliefs, desires to each other. And it is this theory of mind that allows us to make inferences about each other, including commonsensical inferences.
Please write down what you learned in this lesson.
Great. Thank you so much for your feedback.